Hi, I'm Roger Smith, the CEO of Fault Tolerant Technology. And today I want to talk to you about multi-domain computer architectures, hardware and software fault tolerance, and how it can improve satellite reliability. Multi-domain computer architecture is a new computer architecture that really does do things traditional systems can't do. And satellites, particularly small satellites, have had a history of high failure rates, and improving their computer resilience can improve their mission success. Satellites have had a history of software failures, particularly like doing a software update. In 1979, I guess there was a Japanese satellite got bricked on a software update, but another Japanese satellite in 2016 got bricked with a software glitch. And I'm sure we've all heard of the story that NASA lost a $125 million satellite, Mars orbiter, because of a mismatch between metric and English units. Multidomain architecture could have solved all those problems. And all these big mistakes get a lot of press. Small satellites have a much higher failure rate, so today I'm going to focus on small satellites. As we will see, multi-domain computer architecture is hardware and software reconfigurable. So this computer system is built at runtime to meet an application's needs. If an application needs a processor, memory, and sensor, the scheduler allocates those resources to that application for the duration of the application's life. And once the application is over, those resources are put back into the general pool of resources for that computer system. And the ability to reuse and redeploy components and software within this architecture leads to some very interesting features of improved fault tolerance, cybersecurity, and communications. And today, we are going to focus on fault tolerance. But first, a few definitions. We want to define what a single domain architecture is. And a CPU and its range of address spaces is a single domain. So single domain architecture, you have one CPU with one address space. All systems work like this. Every single system works like this. Multiple domain systems is what the name implies, is have multiple CPUs and multiple address spaces. But it's not like a tandem system where everything is redundant and operates in lockstep. In multiple domain architecture, each separate domain has a different task and they cooperate with one another to perform as one system. There are real operational advantages in a reconfigurable architecture, and there are some challenges. Multi-domain architecture is built completely from standard parts, and this is perfect for a CubeSat or a small satellite. The difference between a single domain and multi-domain systems is how components are placed on the circuit board, and this difference creates a productivity gap, so there's a learning curve involved with the hardware design in a reconfigurable system. And because this new design is unconventional when compared to existing methodologies, time and thought is required in how to place and route the standard components in a reconfigurable circuit. So hardware development time and productivity can take a hit in terms of testing and design. We're working on tool chains to help this transition. The software applications of multi-domain architecture is less complicated. And there's no difference between the two systems. The same software will operate on a single domain architecture or the multi-domain architecture. Operating systems still work, although it's easier to implement it either on a bare bones system or a real-time system like RTOS. All of the peripheral drivers still work, all your applications still work, plus you can run simultaneous versions of the software without risk of breaking your system. And above all, there's a significant boost in resilience, which extends mission life, and you can even recover the system to do new stuff. Multi-domain architecture analyzes performance, detects problems, and recovers from faults. In fact, one domain can completely and catastrophically fail, and the other domain simply reconfigures the failed domain from the resource pool until it functions again. Further, the domain controllers, called pads, are FPGA based, and they use the FPGA characteristic to diagnose and self-heal the internal errors, so they're fault tolerant too. And through these self-test and recovery capabilities, multi-domain architecture can provide 100% availability and proactively detect and classify faults while avoiding false and misleading alarms. It is also possible to estimate the remaining life of electronic components and subsystems. You can measure performance metrics like power consumption, heat, and execution times in very unique ways. And because these analytics take place in separate domains, it does not slow down the computing resources performing computation and real-time processing. There's also repurposing. For example, in one mode, different processors are assigned to different tasks like navigation, communication, sensor reading, and such. In another mode, they can reassign these processors to all work together in a compute-intensive problem, perhaps a re-entry or something. It's all reconfigurable. And I won't go into detail, but it does prevent viruses. We view viruses as a special kind of software fault. And it also has a unique form of communication that can easily detect and defeat a man-in-the-middle attack. Small satellite failures can create a space junk problem. SpaceX has launched 12,000 satellites so far, and there are plans for an additional 30,000 satellites to be launched this decade. Now, while they claim a 3% failure rate, that's 1,260 dead satellites weighing 550 pounds apiece in orbit circling the planet aimlessly. Now, some reports have that failure rate down to 2.5%, but that's still over 1,000 dead satellites for this constellation. More of these types of constellations are on the way. One UK company, OneWeb, has proposed a 48,000 satellite constellation. Amazon, for another, in its Kuiper fleet, hopes to launch 3,200 satellites for its constellation. And in 2009, an American and Russian satellite accidentally collided, increased the low orbit debris by 70%. In addition, we have countries blowing up their own satellites to test weapons systems, namely China and India, causing more than 130 million bits of debris in Earth orbit. Other small satellites have a pretty dismal success rate. There are a number of factors that contribute to these failures, and we'll discuss them. But since, kind of the thinking is that since nearly all satellites are launched into low orbit between 160 to 2,000 kilometers, these satellites will eventually and theoretically deorbit in 5 to 25 years or so. The problem is that there are approximately 13,000 man-made objects in orbit right now. And each one is orbiting aimlessly, causing a potential hazard to create more debris through collision with other satellites. Now, a significant cause of small satellite failures is electrical and computer failures, and using multi-domain architecture can meaningfully decrease the number of satellite failures. So here are some stats on CubeSat missions. There are success failure rates on who built the small satellites. And this pie chart shows the crafters. And crafters are defined by experienced builders of small craft who work under contract. So these are semi-professional or professional CubeSat builders. And as you can see, they have a whopping 63% failure rate, and most of which we don't know what happened. And only 5.4 of these were caused by launch. And then we have the hobbyists who have no real experience in the field, and they build these things for fun and future profits. There are no standard construction guidelines for these guys, and the construction thinking is mostly done ad hoc, and these guys have a 71% failure rate. And then we have the industrialists. Now, industrialists are experienced builders of big satellite spacecraft, and they usually build these satellites, the big satellites, under government contracts. And they construct the CubeSats using standard space practices, although some shortcuts. These small satellites are just not their main business. But even these guys have a 52% failure rate. I mean, can you imagine a car company having a 52% failure rate of their car production? They couldn't stay in business. So here's a slide on how many satellites are produced by organizations. As Swartworth points out, it's mostly one and done for CubeSats. So there's a learning curve issue. So, we can go on further and look at the failure rates, but it's interesting to find out that most of them only producing like one satellite, and there's no learning process. You can't learn by your mistakes if you only do it once. This slide shows the causes of satellite power failures. A small percentage of these failures can be attributed to mechanical or material failure. For example, 37% of failures can be attributed to solar array functions. However, 42% can be attributed to circuitry problems. Here is another failure analysis by Siamak Talapozzoli. This study period is from 1980 to 2005, which is dated, but it shows failure by functional systems and it's instructional in terms of where to address the problems. And also, getting any data by functional systems is sparse at best. The AOCS failures are the attitude and orbital control system failures. Now, the mechanical failures were attributed to gyroscope and momentum wheel and thruster failures. However, over 26% of the control system failures can be attributed to electrical or computer issues. Also, of the 20% unknown failures, a fair amount could be attributed to catastrophic electrical failures since no reports were issued on their status. Might be debris or just blew it out of the water, but could be electrical failures. Here's Talapozzoli's numbers on power systems, and he is saying that 67% of a small satellite's power loss is attributed to the electrical system. And there's a very loose association between the Talapozzoli's numbers and the previous slide showing causes of power loss. Talapozzoli's numbers have a larger percentage of unknowns, 12% versus 4%. Evidently, mechanical failures were grouped as payload problems. The bulk of the mechanical failures were payload instruments and things like tethering and docking mechanisms. And the last breakdown he had was the telemetry, tracking, and command systems. And 75% of the failures in this category were electrical or computer in nature. So lumping all these failures together, we get this distribution. In terms of computer electrical system reliability, we see that 51% of all failures is software or electrical. And of the 17% of the unknown, we can determine that a certain percentage of that is caused by electrical or software failures. And I'll estimate that to be 8%. So we can all agree that small satellites have a high failure rate. Roughly 60% can be traced back to electrical or computer-related faults. Reducing the number of electrical or computer-related faults could reduce the number of zombie satellites. Multi-domain architecture can actually bring the failure rate down to something closer to 5 or 10% or even better. And it does it because it really is a better way of producing redundancy. Now, if something fails and you want it to be fault tolerant, you do have to have redundancy. And how you distribute that redundancy can make a world of difference. All single domain architecture design is set in stone when the circuit board is manufactured. This approach guesses at what will break and you try to defend against that. It's not the best approach, but that's how computer systems are designed. That's how you have to design a single domain architecture. Multi-domain architecture erects a computer based upon a process requirements. This means only a minimum number of components required to prosecute the code will be allocated and powered up. So if a hardware component or a code snip is not working, the schedule will just substitute a working piece of hardware in its place. If a code snip goes awry, the scheduler just copies in a canonical piece of code or flags an error. So basically what we have is a bunch of available hardware and software, and we let the scheduler and the L file figure it out. Now we can start talking about a component-based reliability budget. How and where we can deploy redundant components and not subsystems. And there are plenty of options with multi-domain systems. And multi-domain systems work without having to change any of your existing components or software. So if a processor or memory in your present design works, They'll still work in multi-domain systems. Their application code will still work, but you will add redundant components to the new circuit board. And if you want to take advantage of the architecture and new design, there are features that will make it even more resilient. Here is a quick chart showing the typical failure rate of a component or system in life cycle. In the beginning, it has a high failure rate, levels off, and rises at the end of life. And this is similar to what we're seeing in satellite failures. We just have to bring the numbers down. And how do we do that? Through dynamic reconfiguration. This is a software-defined radio schematic I pulled down from DigiKey. It represents a typical single-domain computer circuit made from commercial over-the-counter parts. It could be a solar panel, power controller. It's a typical design that might go into a CubeSat. And there are several single points of failure that would cause the entire system to fail. Losing power to the FPGA, for example, or faults along any of the other components in one of the serial processes will cause that entire process to fail. The standard way to resolve this is through redundancy. So here's the same circuit in dual modular redundancy, basically two copies of the same circuit. And this can either be in hot or cold spares. In space satellites, it's probably going to be a cold spare due to the doubling of the power requirements. So if one system or function fails, the other is powered up to resume its functioning. Not a bad approach, however, there are birthday failures. Now, birthday failure is lifted from a term from exascale computing, where in large server farms, simultaneous failures happen on the two systems. The term is derived from the problem in a room with 35 people. What is the probability of two people having the same birthday? The issue here is that if you have a failure in the primary system and a critical component is lost in the standby system, you have a birthday failure and the entire system is lost. This is the same dual modular redundant circuit in multi-domain architecture. This architecture offers redundancy at the component level and is completely reconfigurable. With multi-domain architecture, we can talk about how to allocate components in your redundancy budget. You can talk about where to place them in the satellite, the number of components on each circuit board. We can even have some components in triple redundancy, others in double, or even no redundancy. And the pad is self-healing, meaning that it can repair its own damaged circuitry. And because multi-domain systems are reconfigurable, this type of dual redundancy is an order of magnitude more resilient than single-domain redundancy. It adds complexity, but is significantly more resilient. We know that around 40% of small satellites fail to complete their mission. Around 25% of small satellites are dead on arrival. That is, that they never work after they are deployed. Around 15% of small satellites fail due to infant mortality. Multi-domain architecture offers a much better resilience than single-domain fault recovery methods, and better resilience can reduce the number of non-functional satellites. Every sports professional, military strategist, or economist knows that you need to change your game plan when circumstances change. Imagine a football team always using the same play for every position on the field. Imagine using a 9-iron to drive a golf ball from the tee and the same 9-iron to use on a putting green. Sports professionals know that they need to adapt their strategy for every game and every circumstance. The same thing applies to satellite resilience. When you use an adaptive strategy, you can change your system for a graceful recovery in different failure circumstances. And using multi-domains architecture, dynamic runtime reconfigurability gives you seamless performance and prolongs a satellite's life cycle. Thank you, and if you want to learn more, contact us.